start. Okay, so this is the last talk of my series of talks in applied model theory. So we've seen, I told you a lot about the model theory of finite fields and of pseudo-finite fields, and in particular, I introduced this notion of I showed that the non-standard counting measure had nice properties, and in particular, it was definable uniformly in parameters and stuff like this. And well, I guess I started telling you things about Zariski closures, and I remember that there were some questions about this. So let me again say what I mean by Zariski closure. So I have a field, any field F, right? And I take a subset S inside F. The Zariski closure of S is, in a sense, to me, it's a sort of abstract object. It's a variety. It's an algebraic set which lives in an extension of F, or for instance, in the algebraic closure of F, or in any algebraically closed field. But basically, you look at the ideal of functions of polynomials in n variables, which vanish on all points of S. And then once you have this ideal, then you look at the algebraic set V defined by I of S. So it gives you a subset of Fn in particular. When you interpret it inside F, it will give you a subset of Fn, which is probably bigger than your S, right? But it also defines an algebraic subset of any field containing F, okay? And by the Nullstellensatz, actually, actually, you don't even need that. But in fact, if you repeat the procedure now with V of F, and you do I and V, well, then you get back on V of F. This procedure goes down one step, all right? Okay, so this is what I call Zariski closure. So the Zariski closure of S, let me write it in, is the set defined by I of S. Okay, so either in F or in some extension of F. All right. And so when I say that the Zariski closure of that something is Zariski dense inside a variety, okay, I really mean that I of S is the same as I of V. All right, that's what I mean. Okay. Right, so the fact that we had this measure gave us certain nice properties. For instance, the fact that if you had a formula in one variable, right, with y bars denoting a set of parameters, well, you know that given a parameter a bar, either the set defined by phi of x a bar is finite and then of bounded size, or it will have a certain measure which is greater than some rational number, okay? So here I'm working inside the affine line, okay? Inside F, if you prefer, giving F measure 1. All right. And so, for instance, we saw that, well, if you knew that whenever you took a parameter that for all parameters a bar, phi of x y bar, phi of x a bar was infinite, well, then this meant that it had measure greater than R. And then that meant that, for instance, you couldn't find more than 1 over R a bar I, such that the phi of x a bar I are disjoint, for instance, okay? The other thing you saw from the invariance was that as soon as a definable subset of some algebraic set had positive measure of an irreducible algebraic set, absolutely, then that meant that actually it was Zariski dense in it. In other words, if mu v of S is greater than 0, then S is Zariski dense in V. Meaning the ideal of polynomials which vanish on S is exactly the ideal of polynomial which vanish on V. Okay, on the other. All right, excellent. So we have all these things. I should say that, so I'm going now to go into the sort of stability theoretic notions one gets out of all these results. So I should mention that many of what I'm going to say is also works for what is called bounded PAC. So if you remember, the condition PAC was that every absolutely irreducible variety has a point, right? Which is defined over the field has a point. So you can, this is a condition, it's a strong condition. I mean, it's a nice condition. Bounded PAC says that if you look at the absolute Gara group of such a field, so you fix a field F, it's going to be bounded if and only if for every n, it has only finitely many Galois extension of degree n. Okay. Now, what happens is that this is a first order condition. The same way we saw that, you know, having absolute Gara group isomorphic to Z hat is a first order condition. To have at most 5 extensions of degree n is a first order condition because you just say it. So which means that if you have a bounded field F1, which is elementarily embedded inside the F2, then this means that the algebraic closure of F2 is obtained by taking the field composite of the algebraic closure of F1 and F2. All right. So anything algebraic over F2 comes from something which was algebraic over F1. That's what I'm saying. And in particular, this allows you to show that bounded PAC modulo adding sufficiently many constants so that you can define all the various Galois extensions, right? This means that the theory of a bounded PAC field will be model complete. So in other words, every definable subset will be the finite to one projection of an algebraic set. Okay, so these allowed, I guess it was first Udi, but then also Udi and Anand, who developed completely the theory of these structures. And they showed that bounded PAC, so let's suppose they are perfect just for simplicity, that they are actually simple and even super simple of rank 1. Okay, so I'm going to tell you a few words about, you know, what are the algebraic, about what is forking, what is non-forking, etc., etc. I should say that, you know, these things really occurred. So the paper on the measures, right, was published, I think, in 90 something, right? In 95, people, I mean, and the bloom of simple theories happened in 95. So many of the results which were obtained by Anand and Udi were sort of front runners of what's going to happen with simple and super simple theories. Okay, but some of these results are really nice, and so I'm going to tell you a bit more about it. I mean, in particular, I'm thinking about the Krell paper, which I really like. Okay, so what did I want to say now? Right, so I told you about, so many of the things that I'm going to tell you in the context of pseudo-finite fields will work also for bounded PAC. A word about perfect. Yes, okay, if you want something to have a rank, it better be perfect, right? you know that when a field is not perfect, let's say if F is not perfect, that means that, well, okay, let's look at Fp of t, and you look at a separable closure, okay? So all the elements which are separably algebraic over this, so in particular, it contains Fp bar, the algebraic closure of Fp, okay? Right, you see that every element, well, if you prefer, actually, you just work over Fp of t, every element can be written as a sum of bi to the p t to the I for I equals 0 to p minus 1. Okay? So here I'm okay. Here I'm in Fp of t. Okay, and this writing is absolutely unique, right? When you go to the separable closure, it doesn't change. It will still be written that way. Okay, uniquely. And so this means that actually, if you have a separably closed field which is not algebraically closed, you will have a definable embedding of F to the P inside F. Now, if you have a definable embedding of F to the P inside F, this really forbids any kind of dimension to exist, right? Because the dimension of F to the P should be P times the dimension of F, right? So you shouldn't have an embedding. Okay, so, but nevertheless, one can still do certain things with imperfect bounded PAC fields. So the theory will not be super simple, but it will still be simple. Okay. Okay, that's a very much apparent. Good. So I'm going to tell you a bit about algebraic groups. So I suppose everybody knows, right? G, an algebraic group. So what is it? So it is an algebraic set, which is meaning it's either contained in, let's say, in Fn or in the projective space over F, right? And it's defined by equations, by algebraic equations, okay? Group, so that's an algebraic set. So then there is a notion, okay, you all comfortable with the projective space? Yes.
Algebraic set be defined by homogeneous polynomials.
Yeah, by polynomial equations. Okay, so quasi-projective means that it's open inside an algebraic set. Yeah. So, for instance, Fn is quasi-projective, right? Because it's isomorphic to some. I remind you that this can be. It's the set of n+1 tuples, right? Which are in Fn+1, not all 0, divided by the equivalence relation of being proportional. Okay, so they are sort of the line directions in An+1. Okay, so you have, since they are all not 0, and since you have this sort of equivalence relation, you can always assume that one of the coordinates is 1. Okay, and then this expresses the others. This gives you, if x0 is equal to 1, then you get an embedding of the corresponding thing inside Fn. Okay, right. So when I say algebraic set, well, obviously you need it to be defined by homogeneous polynomial if you want this to work out, right? And the group law, which is a map from G cross G to G, so the multiplication, right? And the inverse map from G to G, they need to be given by what's called by polynomial functions or rational functions, which are defined at every point and satisfy the usual law. So typical example, GLN of F, or F with addition, or F cross with multiplication. So this is an example of a quasi-projective variety, right? It's an open subset of this, because I took away the point 0, and of course the multiplication is defined a bit differently, all right? It's different, I mean, okay. So anyway, what's happening is that if you have an algebraic group, then the group operations are going to be continuous for the Zariski topology, all right? And this has a lot of consequences. And well, what kind of consequences it has? It has, for instance, that if you fix an element of your G of F, then multiplication by G is going to define a homeomorphism on G of F for the Zariski topology. It also has the following consequence. If you take an abstract subgroup of G of F, just, you know, I don't know, subgroup generated by little g, something like that, right? Take the Zariski closure of that thing, it will be an algebraic subgroup of G, okay? All kinds of things like that. What do I want to tell you now? If U and V are open dense for the Zariski topology subsets of G of F, then U dot V is equal to G of F. Is this correct? I'm always, so I guess F has to be perfect according to my notes. And well, I'm going to tell you. So you know that GV inverse, that G in G, GV inverse is also Zariski dense in G of F. All right. And U intersects GV inverse is not empty, because the intersection of two open dense subsets is non-empty. So that means exactly what we want. So there is U in U, V in V, such that U equals GV inverse. All right. So you have things like that.
Zoe, why did you need it to be perfect, the field?
I don't know. Maybe for something else.
Okay.
Could be that it's for something else. I have a list of 8, 9.
Oh, at least the properties. Okay.
So, that's all. Right. I mean, you have a notion of generic, right? I mean, what's generic? I mean, if you are working in a large field, it's of maximal transcendence degree as a generic of a variety. You have things like that. I'm not going to go much further on this. And I'm now going to tell you a bit more. What happens here? Yes, right. Maybe I should tell you, before I continue on this, maybe I should tell you. So the article, the paper of Axe started the study of PAC fields, all right? So I guess the important people there were Jardin and Kine, who generalized Axe's result to what they called E-free PAC fields. So the Galois group being the free profinite group on E generators. Later to F omega hat, the Galois group on countably many, free group on countably many generators. And then there was a monumental paper by Cherlin, Band, and Dries McIntyre, and at the same time by Yershoff in the 80s, which actually never appeared. What happened is that each author wrote a version and they didn't agree which one was the good version. Anyway, it's a very long paper, and it developed what they called the core theory of the absolute Galois group, which was later more seen, I mean, at least that's the way I see it, as, you know, you view, let's say, you view the algebraic or the separable closure of a field as an omega sorted structure, okay, where the sorts, an element will be in sort n if and only if it is in a Galois extension of the field of degree less than or equal to n. And then you can talk about all these Galois extensions and how the Galois groups act and so on and so on. And you get all kinds of results. And then you can, of course, talk about the Galois group, right? And how it acts. And then you can talk about the inverse system of all these Galois groups. And so you really get a good control of that. And the Muller theory of PAC fields, I guess, you know, apart, I mean, so it's known from results of Duret that there are actually any PAC field which is not separably closed is going to have the independence property. And the reason is just simply because you can code lots of things inside the Galois group. So I mean, the formula that Duret was using, for instance, in the case of pseudo-finite field, was the formula of whether phi of whether x minus y is a square or not. It turns out that you can really, I mean, with when you have y being a parameter, you can really choose anything you want and get something where it will be a square or it will not be a square. So you can easily interpret the random graph in there. Actually, you had later results showing that you can interpret random n hypergraphs in a pseudo-finite field as well, okay? So all these things show you that they very much have the independence property. On the other hand, they are in the case of pseudo-finite fields, they are super simple. They have a very nice measure. They have rank 1. Independence is given by algebraically independence. In other words, forking is given by algebraic forking. So let's say if you have an element A, which lives in some F star, you have some little a. Here you have A inside there. So A is inside F star. Here you have a B. Well, A is independent from B over A if and only if the transcendence degree of A of A over A is equal to the transcendence degree of B of A over B. In other words, there might be some algebraicity relations here, but that's it, okay? And in particular, also what is nice is that, so this is going to be true for any F, which is PAC, is that the algebraic closure of AA is going to be just, you look at the field generated by little a over A, and you took its relative algebraic closure inside F. All right. These elements necessarily need to be there, but that's it. Nothing else is needed. So you see that these are nice properties, right? They tell you that you have a good description of the algebraic closure, you have a good description of independence. So things should work. Okay, so this was the beginning of, as I said, the papers, the results of Woody and Anand were the beginning of really the simplicity and showing that, so this independence relation satisfied the so-called independence theorem, because the forking relation comes from the one in ACF, it obviously has all the good properties that it should have. And in an unstable context, it will be, by a result of Byung-Hun Kim and Anand, it will be the non-forking relation for a simple theory if and only if it satisfies the so-called independence theorem, okay, which is a way of amalgamating three pairs of two types over a model, okay, so that this has to be true. Okay, so these are fairly technical results. I guess first approximation to that results, to those results, were this property which I gave you last time. Remember that, you know, which was called this S1 property, right? The fact that when you had things of positive measure, a family of things of positive measure, then, well, you couldn't have too many of them, which would be disjoint, right? Because, or have small intersection. Okay, so that was called at the time S1 property. It corresponds to finite SU rank. I mean, well, it has connections with Shellar's degree, from what I understand. But since I don't know very much what it is. Okay, so what's time now? 2:30. All right. So last time, I think I mentioned the fact, right, so let me get you some results, okay? Some sort of easy results. And then we'll go to some applications, all right? So they have some very, very nice results, okay? So we have G, algebraic group, defined over F, which is pseudo-finite. Okay, I'm not assuming that G is connected, right? So in other words, as an algebraic set, it might have several irreducible components. As I told you last time, those components, actually, they are translates, they are cosets of a particular subgroup of the algebraic group, which is called the connected component. And right. Okay. So at the moment, I'm just saying it's defined over F, okay? I'm not saying that G of F is Zariski density. I'm not, so it's in particular, it might not be absolutely reducible or irreducible. But if G equals G0, then G of F is Zariski dense in G. That's actually an avatar of the same thing for any absolutely reducible variety. If V is absolutely reducible variety defined over F, then V of F is Zariski dense in F. In other words, why? Because, well, you have F, you look at F of V. Because V is absolutely reducible, this is a regular extension of F, and therefore it's going to embed inside some F star, which is an elementary extension of F. Okay? So therefore it has to be Zariski dense. Okay. 2. If G is connected, then the center of G of F is the center of G of F. And this just comes from the fact that the proof of this is that if let G belong to G of F, and H in G of F-Alg, let's say, such that HG is not equal to 1. I mean, there is an obvious inclusion, right? I mean, this is obviously inclusion. And then what's happening is that you see the condition X in G and X G not equal to 1, right? This defines a Zariski open of G of F, of G, and in fact of G of F. But Zariski open subset of G, it's defined over F, hence it's going to intersect U non F non-trivial. G defined over F, hence intersects G of F non-trivial. You see the points? What is the point here? Is that because this condition is an open condition, that means it's going to be true in the generic extension, okay, in that extension. And therefore, well, it has to be true in F star as well, okay. So, right. So this gives you the results. It's false if G is not connected. Here I used the fact that it's connected to say that because it's Zariski open, it has to be all of G, all right? If not, it would be maybe a subgroup of finite, you know. Okay. What else do I want to tell you? I guess I want to tell you this one, which I really like. Well, okay, so there is the one which is obvious, that H contained in G of F, definable, then its dimension of G of F is equal to the dimension of H. So in the sense of, you know, these numbers mu and d, right, that we associated, if and only if G of F, H has finite index inside H, inside G of F, okay? Well, that's sort of clear. You don't need anything. And the fourth, which I find cute, but it's also trivial, if F from H to G is a morphism of algebraic group, epimorphism of algebraic group defined over F, and with finite kernel, meaning that in some algebraic closure of F, it will have finite kernel, then what? The cardinality of the kernel of F intersected with H of F is equal to the index of G of F inside F of H of F. And I guess here, connected algebraic groups. And you see that, well, if my field F was finite, this would be trivial, right? It was finite of sufficiently large size so that it would have more or less Q to the dimension of G points, right? Then it would be trivial, okay? Excellent. Okay, now I want to give you a theorem which is it's actually something which works also for bounded PSC, doesn't work for unbounded PSC, and it's the following. So I will just tell you. Well, okay, so it's clear that, right. So this is a theorem which says that G be an algebraic group of dimension n greater than 0, defined over F. Let U contained in G of F be definable of dimension n. And H the subgroup generated by U. Then H is definable for finite index in G of F and for some n such that H is equal to U union U inverse to the n. Okay, so in other words, it's a product of at most n elements coming from U and U inverse.
That's different n, right?
That's a different n. M. It's not that different actually, but I mean, there is a relationship, okay, between the two. So the proof is, okay, so it uses the following fact, which is sort of, M. No. 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 No, it has to have symbol. No. This is not Hilbert's indecomposability yet. Okay, so basically the idea is that the proof is to look at the corresponding set, which is the set of G in G of F, such that the dimension of U intersect GU is equal to N. Okay? So we saw that in pseudo-finite field, this is definable, right? It turns out that in fact, in bounded PSC, it's also definable. In fact, in all PSC, it's definable, but it's not as nice in unbounded. I mean, so I mean, this is just saying, you know, that the, yeah, right. Just saying what it is. Right. So it's definable. One shows fairly easily that it has dimension 1, n, simply because you take 2 points of U, which are algebraically independent. You go to a saturated extension, you take 2 points of U, which are algebraically independent. So in other words, they have transcendence degree over n over the base field and over each other. And you take H1, H2 inverse. Well, that's going to be a potential G. Okay? Because it's going to be in those two. Right. So, you know, then you know, because dimension of W is n, you get that a finite number of translates of W cover G of F. Well, that's just because if it didn't, well, you would basically get a contradiction. Okay, that's a sort of tautology I just said, but I mean, if not, well, you start that you would find an infinite sequence so I guess if I do it here, people are not, you find an infinite sequence GI such that if I is less than J, then GJ does not belong to the union for I less than J of the GI plus W times W. Okay. And then you get that GI inverse GJ does not belong to W when I is less than J, but that gives you the other property. You see, and that gives us a contradiction. Well, I think that's it. Okay, anyway. No, I'm sorry, this does not give us the. So it gives us that when I is less than J, then GI inverse GJ is not in W. And this means that the intersection, that the dimension of GI W, the dimension of, by definition, right? The dimension of U intersected with GI inverse GJU is less than N. Right? So in other words, with the measure with respect to G, it has measure 0, right? So we would that way construct an infinite sequence of almost disjoint thing of positive measure greater than some R, but which are whose intersection has measure 0, right? And this doesn't work. Okay. Good. So this is telling you that once you have something which has the right dimension, it generates a definable group. Oh, no, sorry, I didn't quite finish. So finitely many cosets of W cover G, all right? But W is contained in U inverse, right? Or U inverse U. I mean. Okay, so that's it. All right. Now there comes the theorem, which Hilbert's inert composability. It has its analog for, let me just state it, okay, and then I'll stop. It has its analog in super simple theories, or probably even in simple theories, except that it's not as nice. You will see why. So let me state it. So it's a theorem which is true in, I guess it's called true in all superstable theories, right? Was originally proved for superstable theories, or? Okay. Something, yeah. Okay, let me find where I am. 53, 55, 56. For, yes. Mm-hmm. Mm-hmm. Okay, so let me state the theorem anyway. Let G be an algebraic group defined over F, pseudo-finite, and Si, I in I, a family of definable subsets of G of F, which are defined over F. I'm not assuming anything in terms of uniformity, right? Some of them could be points, but okay, maybe the conditions I'm going to say will preclude it being points, but you see. And such that for every I, the identity element of G belongs to Si, and the Zariski closure of Si is absolutely irreducible. Is irreducible. Is irreducible. Same thing. Okay, it will automatically be. I mean, they're equivalent because we are talking about a S set, which is defined a set of F points. Okay. So in other words, you're not going to take things which are two varieties. You are not going to take 2 points. You need to have one in there. So, I mean, you cannot take, say, a subgroup which is generated by a line in F square or things like that, okay? Unless that line contains, is already a subgroup. Yes. Then, H. Consider H to be the subgroup generated by all the Si, has finite index inside H tilde, which is the subgroup generated by the absolutely reducible by the Zariski closure of each of the Si, right? And H is definable, and there are I1, In in I, such that H is contained in the product of Si1 plus or minus 1, etc. Sin plus or minus 1. So, okay, so in other words, not only it's the product of n elements coming from various members of the family or of the inverses, right? But in fact, the members of the family which appear are fixed, okay? Now, how does one do that? So the proof is not, can I do it in 2 minutes? Maybe I can. Yes. First of all, let's start with the Zariski closures, okay? Now this is a theorem, and actually instead of working inside F, we are going to work in the algebraic closure. Okay, so now we take SIZ, we work in the algebraic closure of F. Then it is a well-known result. Okay, it's a result due to Chevalet, which is simply that you see what's happening is that you have closed sets, right? You start multiplying them, right? So if you have S1 dot S2, that's another closed set, okay? And it's also irreducible, all right? So either it has the same dimension as S1 or the same dimension of S2, in which case it's one of the two, right? Because one is in there, right? Or it's not, okay? So then you continue. So at some point, so you do S1 dot S2 dot S3. At some point, well, this is all inside a set of finite dimension, right? Like G is an algebraic group, has a certain dimension. Well, at some point, which is going to be less than the dimension of G, right? It's going to stop, all right? So in other words, if I'm looking at the level of what's happening with the SI, I get an algebraic group H, which is sitting inside G and which has a certain number of things. Okay, good. Now it turns out that this group is, of course, it's defined over F. It's again irreducible. So therefore, well, it's H of F is going to be Zariski dense in it. Okay, and then you show that this H tilde of F, in fact, it comes from this SI Z of F. Okay, so it's really this. Good. So now you take, you know, you have your indices for this H tilde, right? Well, you look at the corresponding products of the SIJs, right? Well, it's going to be of the same dimension as Zariski dense and blah, blah, blah. So same dimension, Zariski dense, and we apply the theorem before, okay? Okay, I'm going to make a break. It's a nice theorem, isn't it? I think it is. It's a break, 5-minute break. 3:35 maybe. Now I was planning to do, yeah, one of the things. Okay, let me wash my hands and drink a bit of water and ça assèche hein, de parler avec la créa. Ça va? Ça va pas trop vite? Non, tu connais ces trucs-là plus ou moins, j'imagine.
Voilà, super, oui, mais.
Il est joli ce théorème. Hein?
C'est assez extraordinaire.
Ouais.
Zoe,
Yes.
I think the first or second field you wrote down was FP of T, right? Ah, here, just above you, over there.
Yes.
What is T? Is it transcendental?
Transcendental, yes.
Then why is every element of the form whatever you wrote on the left?
Okay, do you agree it is true if I'm working with polynomials?
Yes.
Okay.
I mean, wait. For instance, how do you write T? Oh, what is BI? Okay, maybe my question is, where is BI coming from?
BI?
Yes.
Yeah, it's coming from FP of T.
Oh, BI from FP of T, not FP. Okay.
Yes.
Okay.
Why did you write that down? Why did you write that down?
To explain that there was an embedding of FP of T to the P, I mean, of, you know, the products of P copy of FP of T inside FP of T, and therefore couldn't have a notion of dimension. All right. I mean, this is T is what's called the P basis. I mean, when you have a field which is not perfect, you have a notion of P base And basically, it's a smaller set B such that Kp of B is equal to K. Okay, you have this notion, all right? And yeah, that's right. Well, I mean, in that case, the boundary closure is separably closed, the separable closure. Okay. Shall we start again? Everybody's back? I guess everybody's back. Yes, so let me mention something. The reason I like this result is because it really tells you that the subgroup is contained inside something, okay? It tells you something. So you saw that in the proof, it was essential that we had one in each of the SI, right? Because otherwise no. It was also essential that we had this notion of irreducibility, okay? Now, in a super stable context, or in an arbitrary model theoretic context, well, you do have the notion of one being inside a set, but of course you can always add it, you know. You don't have really the notion of being absolutely reducible, okay? I mean, here you see, I'm saying the main part of SI is all there is. I mean, it's not going to be something very big like this, and then a little thing like this, you see? The absolute irreducibility forbids that, okay? This doesn't exist, all right? Good. So in the general case, so in the case of a general super simple or whatever theory, what you get is the following theorem, which is just almost as nice, but not quite as nice, which is saying, so let me get it right. I'm getting, sorry, 53, 57, 57. So corollary, GF as above, SI, I and I, a family of sets defined over F. No, subset of G of F. Then there is a definable subgroup H of G of F contained in the subgroup generated by the SIs, and such that for every I, if you look at the number of cosets of SI modulo H is finite. So how do you do that? It's really a corollary. So you look at SI, you look at its Zariski closure, right? So you know that it's because SI is a set of F points, you know that SI of Z is a finite union of absolutely reducible component and they are defined over F. Okay, because SI was contained in G of F. So you're going to replace, first of all the SIs by their absolutely reducible component. Okay, so in other words, you are going to replace SI. So if SI Z is equal to V1 union Vm, then I'm going to replace SI by SI intersect V1 of F union etc. union SI union intersect Vm of F. Okay, and by definition, each of these is going to be Zariski dense in whatever. Okay. Okay, so now I have that the Zariski closures of my SIs are absolutely reducible. Now I take, so if I have, first of all, if I have G in SI, certainly G inverse SI is going to be contained in the group generated by the SIs, right? Or even by that one, okay? So therefore, I'm going to just translate my SI. I replace, so if GI is in SI, I'm going to replace SI by GI inverse SI. And now it contains the identity. It's absolutely reducible. I apply the previous theorem and I get the result. Okay. I mean, we have that for each I, we know that TI is contained in H, right? Okay. So the finitely many and not just one comes from the fact that here I have irreducible components. Okay. So there might be M many TIs. All right. Okay. Good. So this is the way it appears in the various stability books. Okay. So usually, as Anand was saying, so there has to be a notion of dimension. For instance, you are going to look at groups which have rank omega to the alpha times n, right? And then, well, those SI, there should be, I suppose they should also be big, right? And I guess the conclusion is that the quotient there would be of rank smaller than omega to the alpha, okay? So the failure of getting things is going to be of rank. Yes, super simple of rank omega to the alpha. It's certainly not by me, certainly not. Probably, but I mean, it's as in the super stable case, right? I mean, it's all right. What do we want to do now? I wanted to do an application. Yes, okay. So one application, for instance, is that in the case of pseudo-finite fields or bounded PAC, or in general, so if let G an algebraic GF as above, so G an algebraic group, F pseudo-finite or bounded PAC, perfect. Then if G of F is definably simple, meaning it has no definable subgroup of finite index, then it is simple. And I guess maybe apart from the center, apart from finite Z of G. Okay, so I guess, well, there are several definitions of definably simple or simple in general. Sometimes you allow finite normal subgroups, in which case they have to be central, since their centralizer is going to have finite index and is definable, right? So, okay. Right, and the proof is easy. So of course it's going to be connected, right? Because otherwise, we know also that G of F is not simple. It's not abelian. Why is that? Why is that?
So by simply using there's no definable proper normal structure.
I guess it's defined as simple, not abelian. Because you know, you can imagine that
It's not true for abelian.
it's not true for abelian. Yes. I'm sorry? Yeah, okay. Non-abelian. Non-abelian. It has to be non-abelian. Yeah.
But it makes sense in the abelian context. Let's say it has no normal definable sum. I mean, it formally makes sense. And the point is that if you look at that general context, there's a counterexample for abelian.
Yeah. Yeah, I mean, you know, yeah. Okay, proof. So apart from the finite center, right? So assume H is a normal subgroup of G, any normal subgroup of G, huh? Right? Any normal, right? And infinite, take G or H, which is in H, but which is not in the center. Okay, the center being finite, you can find such an element. And now you look at X, which is the set of G inverse HG for G in G of F. This is a subset of H, right? And in fact, it is because G of F is connected, right? So G connected. You know that the Zariski closure of this thing is irreducible, all right? So the XZ is irreducible. So if now we look at H inverse X, this now contains the identity. And if you look at H inverse X, the group it generates is contained in H and is normal and definable. Okay? So it has to be all of G of F. All right? Okay, there is another result which follows from this, and which is, I find it's interesting. So we will put it in relation with another result of Udi and Anand, which is a nice, very nice result. G, F, as above. We assume that G is almost simple, meaning an algebraic group, simple algebraic group, which means no, I mean, maybe finite center, but no normal algebraic subgroup. Okay, so no normal algebraic subgroup other than the center, which is finite. Okay. Then H, then G of F has the smallest subgroup, definable subgroup of finite index. Okay, so how do you do that? Well, you see, it really comes out of there. So first of all, if you have a subgroup of finite index, right? If you take the intersection of its conjugate, it also has finite index, and now it's normal, okay? So this H is definitely, so let's call it H, it's definitely going to be normal, right? So suppose that G has no smallest definable subgroup of finite index. This means that you can find an infinite decreasing chain of normal subgroups of definable normal subgroups of finite index, right? The intersection of all these subgroups is probably not definable, but it is normal, okay? And the theorem there tells us it's contained in a definable group, okay? But now compactness tells you that this is impossible, okay? So, I mean, this subgroup has infinite index, right? It contains a definable infinite normal subgroup, which automatically will have dimension less than the dimension of G. Therefore, its Zariski closure will have dimension less than the dimension of G, and this will contradict the simplicity of G. All right? So this gives you the theorem. And why is it such a nice theorem? It's because of another result of Anand and Doody, which says the following. So let me write it here. So we have G and F as before, and let H be a definable subgroup of G of F of finite index. Then, actually, G is just an algebraic group. Okay, it's not as broad, but G algebraic group. Okay, over F. Then there is an algebraic group G tilde and an isogeny G tilde to G defined over F, everything defined over F. Such that, so isogeny means that in the universe of algebraic groups, this map is onto and has finite kernel, okay? And such that, well, if you look at the image by F of the F points of G tilde, this is contained in H and of course in G of F and has finite index. in G of F. Actually, we know what index it has, right? I mean, we know it by the counting measures. But even in the case of bounded PAC, this is true, and without having the measure to help us to compute the index. All right. So you see, right. Now you see what this tells us? It tells us that at least if we are working with finite fields, right? First of all, we know that when we have an isogeny like this, right? We know that it's not going to be on 2, right? We know that the index of the image of G tilde of F will be greater than or equal to the size of the kernel intersected F, right? Right? We know that. It would be actually equal. So therefore, we know that when we have something like that, unless F is somewhat injective on G tilde of F, right? Its image will be a proper subgroup. So this is actually telling us, it gives another proof of the fact that if you have an almost simple group like this, there is a sort of largest, almost simple group, G tilde, which projects via an isogeny onto G. And this is called the universal cover of G or something like that, universal, right? Universal central extension. So there is a unique one. So it's funny how, you know, this going around, this gives you another proof of this well-known result, okay? How am I doing? So I have 10 minutes left. Okay, let me give you something which is nice. An application, completely different. I'm thinking because, you know, now I'm thinking because I'm afraid. Okay. So I'm not going to do the algebraic details of what I'm going to tell you. I mean, you know that when you work inside matrices, a group of matrices, right? You have a notion of unipotent elements. So basically, what are the unipotent elements? They are elements which have one on the diagonals. They are upper triangular matrices, okay, with one on the diagonals, okay? So if you are inside Gn of F or Gn of K, Gln of K, well, you know that if you have such a matrix, if you take the cent power, I think, if you take this matrix minus the identity element, right? So now you have to transform it into something with zeros on the diagonals, right? And maybe non-zero entries above the diagonals. You take the nth power, you get something which is 0, okay? So in other words, we can define what are things which are log and exponential. So given a unipotent matrix, so we work in GLN of F, right? F any field for the moment. So U unipotent. So think of it as one on the diagonal, and then you look at U minus IN. You raise it to the n, this is the identity, okay? And so you are going to define log U to be U minus IN plus minus U minus IN square over 2 plus etc. plus minus 1 to the n minus 1 U minus IN to the n minus 1 over n minus 1. In other words, the usual formula for the log, okay, except that we stop at it's zeros here, sorry. And given, and if V in Mn of F is nilpotent, meaning it corresponds to one of those guys, in other words, V to the N equals 0, then you define X to V equals V plus V squared over 2 factorial plus V cubed over 3 factorial plus Vn minus 1 over n minus 1 factorial. Okay, so you get to the bijection between the unipotent matrices and the nilpotent matrices. And if U is unipotent, you can define X of UF to be the set of X of T log of U, where T is in F. So you see that this is definable, right? Given U, this is going to be definable. So given U, we know that, yeah. Excellent. And it's isomorphic. So it is a subgroup of GLN of F, which is isomorphic to F plus. Okay, because the exponential, you know, exponential over sum is the product of the exponentials. Good, I'm not showing it. This is. Hmm? Oh. Thank you. And I'm getting near to the end now. Right. Now, in particular, if my F was FP, right, was the group on P generators, the field with P elements, you would get that it's a subgroup isomorphic to, it's a subgroup of order P, right? And actually, the theorem is the following. So it's a theorem which, if I remember well, it's due to Norrie. So we proved using ultra products, and it's nice. Theorem, let n greater than 1, it's an integer. There is k such that every subgroup G of GLN of FP, which is generated by elements of order P, is of the form subgroup generated by G1, etc., times subgroup generated by GK, where G1, GK are in G. And furthermore, there is, I'm not going to do all that. There is D, which is D of n, such that if G star is the algebraic subgroup of GLN of FP alg P bar generated by the elements by the X tilde of U, which are, remember, this is the X of T log U for T in a pH, but U belonging to G and of order P. Okay, so what am I saying here? You see, I'm looking at a certain family of X tilde of U, right? So each of these groups is definable. They form a family. I'm not going to consider all of them. I'm only going to consider those which come from element of G. G, here, G, right? Okay. Then G star, the index of G inside G star of Fp is less than or equal to D. And in particular, if P is greater than D, then all the elements then equal. It's a nice result, right? So I guess I'm going to have time. Do I have time? Do you give me 5 minutes? I started late. I'm going to do the first half, okay? Yes, I mean, if P is greater than D, then in fact, it's equal. If P is sufficiently large, those two groups are equal, okay? That's right, I'm not saying it's right. Okay, so how do you do it? You suppose this is not true, and you find a sequence. You enumerate all the possible formulas, and you find a sequence of primes which contradicts this statement, okay? So let me do it quickly. So first of all, we look at phi of xy, which expresses that y is unipotent. Okay. And there exists a t in F such that x is equal to xt log y. Okay, so this is exactly defining the subgroup X of YF, right? Okay, so fine. So and whenever Y is a unipotent, if B is a unipotent, then phi of XP defines a subgroup. And its Zariski closure is irreducible, okay, in F pseudo-finite. Suppose there is no such K. So find a sequence P of I, increasing sequence of primes, and for each I, a subgroup, a subset AI of GLN of F PI of elements of order P to the I, such that if you look at GI, which is equal to AI, cannot be written as A1 as the product of I cyclic subgroup where A1, AI in GI are have order PI. Okay, so it's just the compactness. So then we look at the structure Mi, which is just Fp of I and plus times Ai, right? And we lay with that N, which is F plus times A, an ultra product, non-principal ultra product. Okay. And so then what do you get? So we know that AI, so it consists of elements of order P of I. So this means that it consists of unipotent, unipotent or unipotent? Unipotent or unipotent? Unipotent elements, right? Because AI to the P to the I is equal to 1. And so therefore, so is A. A is going to consist of unipotent element, all right? And on the other hand, we know that for A in A, we know that X of A, which is the subgroup defined by G of A, right? By phi. We know that this is a subgroup, additive subgroup of GLN of F. And it has, for Zariski closure, exactly the what it should be, right? The exponential of T log A, where T is in the algebraic closure of P. Okay, so we have an infinite family of subgroups. Subgroups whose Zariski closure, which are connected. So by the theorem, we know that actually the group they generate is generated by finitely many of them, right? So in other words, we know that the group generated by all the X of A, Z, by all the X of A, is going to be X of A1, X of A. Okay. So now already we have a contradiction with what we had assumed, right? Because my R is going to be the K, which is there. Okay, this is going to be true for almost all of them. The thing about the finite index, is just going to be from the fact, if you look back at the proof of how it goes, right, of how the proof was done, we had actually proved that our group had finite index in the Zariski closure, right? And so that index will have, of course, will be bounded and so on and so on. Okay, I'm finished. I hope it made you want to read this paper by another Nudi in Krell. It's a nice paper. It has other applications which are similar in nature, and they're very, very nice. Any questions? Bon.